Atoms are made up of three different subatomic particles: protons, neutrons, and electrons. In the center, the protons and neutrons clump together to form a nucleus. The electrons swarm around the nucleus in an electron cloud. We cannot know where an electron is around a nucleus, but they are most likely to be found in shells. Each shell is made up of subshells, S, P, D, and F, and each subshell contains one or more orbitals. Each electron inside an atom has 4 quantum numbers. The principal quantum number, represented by an n, indicates the shell or energy level. The higher the value of n, the further the electrons are from the nucleus and the higher their energy. For example, if n is 1, then the electron is in the 1s shell. If n is 2, then the electron is in the 2s or 2p shell. If n is 3, the electron is in the 3s, 3p, or 3d shell. And if n is 4, the pattern continues. The second quantum number, the angular momentum quantum number, represented by a lowercase l, represents the shape of the orbital. For example, if L were to be 0, it would be the s orbital. If L were 1, it'd be the p orbital. If L were 2, it'd be the d orbital. And if L were to be 3, it'd be the f orbital. The third quantum number, represented by m sub L, is the magnetic quantum number, which represents the orbital orientation within a subshell. For example, if L were equal to 1 in a p orbital, it'd be in this orbital slot. In a d orbital, L could be equal to 2, it'd be this orbital slot. The 0 will always be the middle orbital, and everything to the right is positive, increasing, and everything to the left is negative, decreasing. The fourth quantum number, represented by m sub s, is the spin quantum number, which can have two values, either positive 1/2 or negative 1/2, and this determines the direction of the electron spin. Every single orbital inside a subshell has 2 electrons, each with opposite spins. No 2 electrons in the same orbital can have the same spin. So putting this all together, the 2p3 electron of nitrogen in this orbital would have a principal quantum number of 2, since it's in the second shell, an angular momentum quantum number of 1, since it's in the p subshell, the magnetic quantum number of positive 1, since it's in the third orbital of the p subshell, and a spin quantum number of positive 1/2, since it is spinning upwards. Each orbital inside a subshell contains 2 electrons at most. An s subshell contains 1 orbital and holds 2 electrons. A p subshell contains 3 orbitals and holds 6 electrons. A d subshell contains 5 orbitals and holds 10 electrons, and an f subshell contains 7 orbitals holding 14 electrons. Electrons always fill subshells from lowest to highest energy, and they fill orbitals from left to right. First, putting 1 electron spinning upwards in every single orbital inside the subshell, and then a second electron spinning downwards in every single orbital inside the subshell. The order in which electrons fill subshells is 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s, then 4d, then 5p, then 6s, then 4f, then 5d, then 6p, then 7s, and so on. Now, this order is pretty convoluted looking, and you're probably not going to remember this. But don't worry, because this order is based on the periodic table. The S block is for groups 1 through 2 plus helium. The P block is for groups 13 to 18. The D block is for all transition metals from groups 3 to 12. And the F block is for this block down here, representing the lanthanides and actinides. The S subshells start at period 1, going 1s for period 1, 2s for period 2, 3s for period 3, and all the way down. The P subshells start at period 2, with period 2 being 2p, period 3 being 3p, period 4 being 4p, and so on. The D subshells start at period 4. However, the notable difference here is that for period 4, the D subshell is 3d, and then 4d for period 5, 5d for period 6, and 6d for period 7. The F subshell is once again different, starting at period 6 with 4F, and then period 7 with 5F. Chemical bonds are attractive forces that hold atoms together in compounds. There are three main types. Ionic bonds are formed between metals and nonmetals. Electrons are transferred from one atom to another. Metal loses an electron, and nonmetal gains an electron, forming a positive cation and a negative anion, which attract each other. For an example, table salt, or sodium chloride, where sodium loses an electron and chloride gains an electron. This is strong due to lattice energy, which is the energy required to break the ionic crystal. The second is covalent bonds, which are formed between two nonmetals, where an electron is shared between them. This can be both nonpolar and polar. For example, water, H2O, has polar covalent bonds, where the two hydrogens share an electron with the oxygen. The third type of bond, the metallic bond, occurs between metal atoms. The valence electrons between these atoms are delocalized and free to move through a sea of electrons. This gives metals conductivity, malleability, and ductility. Hybridization happens when atomic orbitals mix to form a new hybrid orbital for bonding. Common orbital types are sp for linear bonds, sp2 for trigonal planar bonds with an angle of 120 degrees, sp3 for tetrahedral bonds with an angle of 109.5 degrees, sp3d for trigonal bipyramidal bonds, and sp3d2 for octahedral bonds. There are two types of bonds, sigma bonds and pi bonds. Sigma bonds are the first bond formed between two atoms, formed by head-on overlap of orbitals, s overlapping s overlapping p, or p overlapping p. These sigma bonds are stronger than pi bonds due to greater orbital overlap and formed in all single bonds. These allow for free rotation around the bond axis and less restricted by other factors. Pi bonds are formed after a sigma bond in double or triple bonds only, created by side overlap of p orbitals. These are weaker than sigma bonds due to less effective overlap and prevents rotation around the bond axis. A double bond is one sigma bond and one pi bond, and a triple bond is one sigma bond and two pi bonds.